back doing part 2, starting on multiple choice 20. It says ammonia is least soluble in which of the following? So we're going to be doing like, dissolves, like here. Ammonia looks like this. So it's polar, which means that it's got hydrogen bonding because we have hydrogen bonded to either N, O, or F, and that's the one we have going on here. So we're looking for somebody else who's polar. Oh, least soluble. So we're looking for somebody who is the most opposite to this. Water looks like this. So this has H bonding. That's very soluble in it. We all know about carbon tetrachloride. That's nonpolar with London. There's going to be the answer. That's got a hydrogen bond there, HF. There's a hydrogen bond. And this one is polar with no hydrogen bonding. But polar is going to dissolve polar a lot better than polar would dissolve non-polar. So the one that's the least soluble is going to be the non-polar one right there. Make sense? Yeah. According to the theory behind molecular shape, blah, 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 blah. All they want to know is why does the bond angle decrease when you go from that to that to that. Okay? No lone pairs, one lone pair, two lone pairs. So the number of lone pairs increases. Lone pairs can also be called unshared electrons. So I'm looking for these words. That's it. That is the one thing. The lone pairs. You know, this theory is actually called, has a name called the SEPR, valence shell electron pair repulsion. The valence shell electrons are repelling the electrons in the covalent bond, the sigma bond. So, not mentioned there, not mentioned there, not mentioned there. Increasing number of lone pair electrons on the central atom. Perfect. There it is. Only place it was mentioned. Okay. Which of the following is least soluble in water? So this is an alkali metal, it's soluble. This has a nitrate, soluble. This is an alkali metal, soluble. Alkali metal, soluble. So the answer is BaCO3. Decrease in entropy. Okay, that means this is going down. Another way of saying it is this is less than 0. So we're looking for something that gets clean. I should have put a G on here, and the answer is E, because this one goes from a solid plus a gas to a solid. All the others either don't change in state or actually get messier. So the answer is E in this case. Types of hybridization in this molecule. Let's draw out the Lewis structure for it. Looks like this. C connected to C with 2. Now we got to go and fill everything in so that, ooh, this is an H. So if we do that, we got it. This one is sp3. It's got 4 things around it. This one is sp2. It's got 1, 2, 3 things around it. And that carbon is sp2. It's got 3 things around it. So there's only sp2 and sp3. Seems to be a theme in these problems, making it 2 and 3. 25. The ionization energies for element X are listed above in the table. So we're looking for jumps. And in this one, we got a jump, and we got a big jump right here. So it's between 3 and 4, so it will lose 1 electron. It'll lose a second electron, it'll lose a third electron, but not allowed to lose a fourth. So losing 3 electrons makes you 3 plus, and aluminum is the only one in here that would be 3 plus. Which of the following molecules has the greatest dipole moment? The most polar. That's going to be SO2. A little bit tricky, but when you draw the Lewis structure for SO2, you end up with this. So it's the only one with a lone pair on the central atom. Everybody else is either linear or nonpolar tetrahedral. Let me go over how to do this one more time, because I think some people are a little confused on how to shift. So you got these electrons. Okay, so we're going to attack one element. Okay, we hit a dead end. You cannot split these because you would be splitting to a double. Or you can think about it, the only time you can split is to hydrogen or halogen. So we're going to shift over here to this oxygen, thus opening up this to bond. And that's where we end up with this. And this structure actually does have resonance, and it's important to get in the habit of always drawing the resonance structures. If we were to take the average, we could think about that pi bond is distributed over the whole thing. And you have like 1.5 bonds right there. One way to think about it. Okay? In the periodic tables, the atomic number increases from 11 to 17. What happens to the atomic radius? Alright, so as you go this way, okay, size goes down. And it goes down because you're staying in the same energy level, but you're increasing the number of protons, thus you're increasing the strength for which the nucleus is pulling on those, and everything gets smaller. So it decreases only. Never increases than decreases. Okay, 28. Let me go here to my key to do 28. A little bit tricky problem. So in this one, let me find this. Hello. Okay. The answer is A. And let's go over how I got that. Okay, according to the information above, what is the standard reduction potential for the half reaction M? So we're looking for the reduction potential of M, what it would be on the chart. So we know that E equals negative E ox plus E reduced. The total E is 2.46. So 2.46 volts equals negative E, and M is oxidized, plus E, Ag is reduced. Okay, so 2.46 volts equals negative E, M, plus 0.80 volts. Now, when they say the standard reduction potential of M, what we're looking for is we're looking for the initial M. We're looking for this. Because when you flip it, that's what makes it oxidized. So we're looking for it without the negative on it. So you're going to go 2.46 minus 0.80 is 1.66 volts is equal to negative EM. And we want EM, we want what it was on the chart. This is what made it oxidized. So negative 1.66 volts equals E for M. And that's the reduction potential. It's a tricky problem. I want to look at that a couple times. Okay, when the equation above is balanced using low cell number ratio, blah, blah, blah. Figure it out. So start with the carbons, 2, hydrogens, 3. So you got 7 total oxygens on this side. If I put a 3 here, it gives me 6 plus 1 is 7. So 3. Alright, we got our little battery here. Let's go ahead and label everything we can on the battery before we start. There's the anode, there's the cathode. Electrons go in that direction. So in the above picture, called the Daniell cell, the voltage is shown. Shown above is what? So we know the voltage is negative E ox plus E reduced. Who's being oxidized? Well, we know that an ox red cat, so the anode is going to have to be oxidized, and in this case the anode is zinc. So negative, the value for zinc, I believe it's negative 0.76 plus 0.34 equals 1.10 volts. So this actually shows up a lot. The Daniell cell's standard battery of zinc and copper. That's why I tend to ask that problem a lot. So the answer is B. All right, guys, going to stop this and move on to the free response.